In this video, I wanted to go over electron configurations. So the periodic table is beautifully set up such that it can lead us to how to set up an electron configuration, or another way to say that is it can lead us to a way to show where all of the electrons are quote-unquote placed in their atomic orbitals. Okay, so we've already talked about how the atomic number, right, this whole number that's at the top of each of the elements boxes, right, that indicates how many protons are in the nucleus. And remember, for a neutral atom, the protons are equal to the electrons, all right? And this is just in a neutral atom. Okay, so we can actually use the periodic table also, in addition to determining how many electrons will be associated with that atom, we can also use the periodic table to determine what our principal energy level is. Okay, so the rows, or the periods, are good starting points for where the principal, or what principal energy level an electron will be in. For instance, the row 1 here, containing only hydrogen and helium, right, period 1, this has a principal energy level of 1s, okay? 1s for its principal energy level of 1. And as you go down, the principal energy level associated with period 2 is 2. The principal energy level associated with period 3 is 3. Principal energy level is 3. So we can use this information to get to how the electrons are arranged. Okay, so say for instance, if I take helium, okay, if I look at helium over here on the right side of the periodic table, okay, I know that it has 2 protons. For a neutral atom, it must have 2 electrons. So in order to determine which one those are in, we start with the lowest principal energy level, which is 1s, okay? 1 being the principal energy level, s being the orbitals that it's going to go into, or the subshell that it will be in, okay? So, and remember, each orbital, right, each orbital can only contain 2 electrons, and the s only has 1 orbital associated with it. 1 orbital here. So both of the electrons that are coming from the helium atom, right, 2 electrons here with the neutral atom, both of those electrons will be quote-unquote stored in, right, stored in a 1s orbital. So then you write the electron configuration as 1s2. The 2 here indicates the number of electrons in that orbital. Okay, and in S subshell's case, it's the number of electrons in the subshell as well. Now let's look at an atom where we venture out of the 1s orbital. That is to say, we go beyond the principal energy level of 1. Okay. Now let's look at beryllium here. Beryllium, notice it's in the second period, right? So its principal energy levels will contain a 1s and a 2s. Okay, the 2s, because now the 2 is indicating that it's in the second row, right? The second row here, or the second period, and the s is indicating that it will only have 2 electrons that will go into that s subshell. Now, why is that? That's because the 4 electrons that are associated with beryllium, remember we have four electrons here, 4 protons, neutral atom, so we have 4 electrons. 2 of those electrons went into the 1s subshell. Okay, notice this 2 right here. Okay, that 2 indicates that there are 2 electrons in the 1s subshell, so that one's full. So then the electrons, the 2 more electrons needed somewhere to go, so they go into the next principal energy level, which is the 2s. Okay, so then we can write 2s2 here to indicate that we have 2 more electrons in the s subshell in the second principal energy level. And then we can check our work. We said that beryllium will have four electrons, right? 4 electrons. So we have 2 plus 2, 2 plus 2, so I'm moving my whole periodic table there, 2 plus 2 equals 4. Good, so we've accounted for all of our electrons. So now let's keep going to get to a p subshell. Let's fill in the p subshell. So the p subshell is a slightly higher energy than the s subshell. So say if we are placing the electrons in a carbon atom here, right? So we're going for 6 electrons total, right? Because 6 protons, as its atomic number indicates, there are 6 protons, neutral atom, 6 electrons. So we can take those electrons and we start with, and notice that carbon is in the second period, so we're going to get to a final destination, if you will, of the second principal energy level. Okay, now we have to fill in the lowest energy atomic orbitals, and we have the 1s, and remember, only 2 electrons can fit in there. And then we have the 2s, and only 2 electrons can fit in that subshell as well. But now we've come over to the p over here. Notice how we're in the p subshell, the p block over here. Okay, so now we could start filling in electrons into the p subshell. And remember, the p subshell has 3 orbitals in it. And remember, each orbital can contain 2 electrons, okay? So in the p subshell, if it were full, it could totally hold, hold a total of 6 electrons, okay? 6 electrons total in a p subshell. However, carbon here, 4 electrons have already been quote-unquote placed, okay? 4 electrons are sitting happy in the 1s2 subshell, or excuse me, 2 electrons are sitting happy in the 1s2 subshell, and then the 2 more electrons are sitting in the 2s subshell, okay? So now we have 2 more electrons we need to account for, okay? So those 2 electrons will come up into a 2p subshell, okay? But because there are only 2 more electrons left, you put the 2 right there at the top. So now we can check ourselves to make sure we've accounted for all 6 electrons for carbon. We have the 2 electrons in the 1s subshell, 2 electrons in the 2s subshell, and 2 electrons in the 2p subshell. So now we've accounted for 2 plus 2 plus 2 equals 6. So we've accounted for all 6 electrons. Now let's go further down the periodic table and see how we can use the periodic table to help us fill in the electrons and to make the electron configuration. Okay, let's go over to sulfur here. Sulfur. So it is in the 3rd period, so we know that the final, since it's a main group element, we know that the final principal energy level it will be in, or that we'll write in our electron configuration will have a 3 in front of it, okay? And we also know, since it's in the p block over here, we know that the final electrons that we'll be accounting for will be in the p subshell. All right, so let's just start from the beginning. So you can utilize the periodic table, right? So you can indicate that both the first 2 electrons will go in the 1s subshell, right? So you write 1s2. Okay, and now we need to go to the next energy level up. They'll be filling in the 2s region, which are equivalent over here on the left-hand side of the periodic table. So we have 2 electrons going into the 2s subshell. Okay, and then we come across the periodic table to fill in the p block here, right? So 1, 2, 3, 4, 5, 6. That beautifully gets us to 6 electrons filling in the p subshell. So we write 2 P6, okay? And now, so we've gone through, accounted for the first row of electrons, the second row of electrons, now we're down to the third row of electrons. And since sulfur is over here with its 16 electrons, we'll come to this side and account for these two. Now these two will go into the 3s subshell. And so we write that in our electron configuration, 3s2, okay? And then we're still not done, right? Because now we need to come all the way over here to sulfur. And so we have 1, 2, 3, 4 electrons in the P subshell. See how we came across the periodic table and quote-unquote filled up our subshells by just counting the number of or how far over it is from the left. So we have 1, 2, 3, 4 electrons in that final P subshell. So then our electron configuration gets rounded out, accounting for the last 4 electrons by writing 3p4. Now, we know that based on the atomic number, it's going to be 16 electrons, right? So 16 electrons, let's account for all 16. If we have the 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, and then plus 4 more is 16. So we have accounted for all 16 electrons. And that is how you write electron configurations for main group elements.